That's okay. The people who come, we make the lecture for them. Okay, let's get started. We were thinking about making a pipeline architecture. Last week we did a single, no, you don't really want it. Okay. I truly believe there are much more entertaining things than this lecture, but we have 2 hours. You paid me a lot of money to give this lecture, so, you know, I want to earn my salary, exorbitant salary, and people are watching online and they're saying, hey, we are sitting here in our pajamas or in July sweating, and we want to have something for our lecture. Okay. So, what was happening? Oh, sorry.
Maybe you should pay your assistant to help you yesterday.
Maybe I should. But you know, I'm a cheapskate. I see half? No. Where's the other? You're missing one. Okay. The most important person is here. He didn't cut himself. He's still alive. I mean, okay. Attempt number 3, serious lecture. So, where are we? What are we doing? So from the beginning of the lecture, we said we want to learn how processors, computers work. We said that this is going to help us in your studies, in working in computer science, because the more you know what is happening behind the scenes, that might help you make decisions further in your career when you are evaluating, shall I do it this way, that way, having an understanding of what happens inside the computer may help you make better decisions. So this is why we started. And in the beginning, we were keeping it a little bit boring, maybe. We had transistors, what's that? We don't like them, okay. Then we moved to gates. They looked very simplistic. We went to combinational logic. All the while, our goal was we will use these things to put together a processor. And believe it or not, the one that we did last week, a single cycle 32-bit processor, is actually quite a decent thing. I mean, it's much, much more advanced than anything that went to the moon. Okay? I mean, people were able to go to the moon without doing this. People were actually anything that predates 1990s did not use a processor that advanced that you can, with a little bit of effort, actually write a code yourself, implement on the FPGA that you use in your exercises. So there is enough power, enough computing resources in that processor that we can design. So we said that RISC doesn't have too many instructions, which makes it easier to implement. So instead of 600 instructions, we maybe have 60. Those are small, tight instructions, but by combining them in different ways, we can achieve more complex things. Then 2 weeks ago, we were talking about the instructions, how they come together, what type of things we have. And then last week, we finally put things together. We said, hey, everything starts somewhere in the memory. So we said the program will get compiled into ones and zeros in the memory. I'll keep referring to this one, so let me just throw it shortly here. There's a part of a data memory. It has addresses that start from here somewhere at the beginning and then go all the way to whatever, F0. And somewhere here is our program, and we have a program counter that points to this location and says, this is the part where there is the program that will tell us what to do. There's one instruction, and the way that we work with it is we fetch one instruction, look what it does, decode it, fetch the operands, do what we are supposed to do, write it back. Now, we did this, and in the end, we also calculated how fast this thing was working. Because we are doing these processors, and the difference between one processor and the other one ends up being which one does things faster for us. And behind all the marketing talk, we argued that this is the one thing that tells us the most. Our program will get compiled into a number of instructions called N. Our architecture will be able to take some clock cycles to realize one of my instructions. And then the next thing is every instruction will take some time to realize, because there's logic in it, that logic has propagation delays, yada, yada, yada. So the more I have to do, the more time I have to give. And this time will tell me how frequently I can repeat it. So either it's the period or 1 over frequency, how often I can repeat it, comes into this formula. So if you're looking at it, and this is the argument we made, if you're not happy with your processor's performance, you can do 3 things. And this still holds true. This is, I mean, it's as basic as this. So when you are comparing, I don't know, great company product X to another great company product Y, it will boil down to this, no matter what they write in Tom's Hardware or something else. So you can reduce the number of instructions. You can do this by either having instructions that do more, combine things so you don't have to execute so many instructions, or what's more often the case is the hardware is actually capable of doing some miraculous things, but not everybody is a hardware architect, doesn't know the details better. So we require compilers, we require some tool support that translates our ideas into those instructions, and maybe we need to spend some more effort in those compilers. So those are the 2 things that would reduce N. Now, it's not always goes in the same way, and this was already pointed out. We can use less cycles to perform the instruction. Make the instructions work faster usually is the opposite of the first thing we are trying to do. So make instructions that do more, well, ends up sometimes requiring instructions that also take multiple clock cycles. So simpler instructions would be better to reduce the clocks per instruction. And the other thing is, you know, I fetch one instruction, I work with it. Why don't I do multiple things? Why don't I have multiple instructions at the same time? Why do I only do one? Let's hire as many ALUs, decoder units, fetch units as we can. Seemingly transistors are for free. Moore's law makes sure of that. So I can use multiple units in parallel. The other thing I can do is, so if I manage to do this once per nanosecond, why don't I speed it up? Why is it taking so long? Maybe I can redesign the time-critical components and find a better implementation. Maybe I can find a newer technology, pay another company to manufacture my chips. So the idea is entirely the same. Just by virtue of better, nicer, cuter transistors, everything will magically work faster. And the other one that we started talking about yesterday was adopting a technique called pipelining so that I can increase the clock frequency while not changing the functionality. And for the rest of this lecture, we are actually going to discuss about these things, nothing else, essentially. We may not see this slide so often, but we will realize there are certain problems with the single cycle instruction that we explained. Single cycle instruction single cycle architecture for MIPS works. There's nothing wrong with it. It's just that we can do better if we are prepared to pay the price for it. And it's important to understand what are the issues so that we can balance, is this price really worth it or not? So before we go any further, here is what the problem was. We looked at the single cycle architecture, and like any digital circuit, this is not different. It has these fancy boxes and things, but essentially we have a clock that launches a new program counter that fetches something from the memory, we find something from the register file, we go into an ALU, do some sort of operation that gives an address, we go to yet another memory, we read the data that is finally going to be the end result, and we bring it back to the register file, which is a clock and a write enable, so we finish it. Now, this entire thing, how long does it take? Well, This is the cycle time, so TC, and there is a propagation delay of this thing, propagation delay of this, propagation delay, another one, another one, another one, and then before writing to the register, we have to make sure that it has to come a bit earlier. I can't go faster than that, unless, of course, I find a magical replacement for one of these. So I've already, let's say, hit my limit. I found someone who makes me a good memory. I found someone who makes me the best thing. The other thing to look at it is, when we sum these up, some of these operations are more difficult than the others. Like there is a sign extension here. It takes a 16-bit value, makes a 32-bit value. What do you say? Is this a difficult thing, or is this something that would make our processor spend a lot of time? Anybody, any idea what we do here? Someone says this? No? Okay.
We just add some zeros or ones.
Yeah, we look at the most significant bit here and copy this bit to the rest of the missing 16 bits. That's like as simple as it comes. There's no, I mean, not much time is lost in this. I just take this, whatever this bit is, please copy it to the next ones. And it's not like a copy operation. It's like that wire, instead of going to one output, goes to 16 outputs at the same time. This is a almost no time operation. Whereas we frequently talk about it, we also discussed this a little bit, but trying to find a data in the memory, given an address, trying to find this data takes a lot of time. This will haunt us. We will have nightmares because of this. And starting next week, Ataberk is going to show you a lot of tricks in which modern processor systems cope with this long delay here. The big secret is, up until like 1980s, people were making processors like this, and then they suddenly realized we cannot keep up. This thing is so much of a bottleneck, we need to find a different solution. Now, for the moment, let's forget it and let's say, hey, this is working nice, but still, when you go to the next slide, you will see that the memory reads are by far one of the longer operations. In fact, when you look at the setup time, that's like 20 picoseconds. Granted, these numbers, who knows how accurate they are from a textbook for didactic purposes, but there is an order of magnitude difference between, let's say, the multiplexer, the register to clock delay, and the ALU or memory read. So these things are big chunks of what is happening, and it's a little bit hard to reduce them just by the nature of these things. So then we sum them up. We have here the numbers. So in a case where we ask this in the exam, what you have to do is identify the critical path, look up the things and find the correct propagation delays. If you're asking setup, contamination delays, if you're asking hold, and sum them up. And you say, sure enough, I pick one this guy, two memories, one register file read, a MUX, one ALU, and a setup. Sum this up, I come to a value. That says, in the worst case, if I'm executing an instruction, I will need 925 picoseconds. After that, I'm done with it, no matter what the instruction is, because this was the worst thing, this was the most difficult thing that I could calculate given this architecture. Now, how did I know this? Well, I spent some time, I designed it, I realized what's bothering me. I also had maybe some tools. So it's not, when you have it, it's not immediately screaming at you in your face. You still need to perform some time to analyze it. If I'm being creative and in an exam, I give you an architecture that is slightly different, maybe. Not, there might be different paths. There might be a strange instruction called Bugu, which does all kinds of weird things and does 5 memory lookups or something like that. In that case, that thing will be different. Okay, you're thinking whether or not I'll ask it. Okay, me too. So what we cared was, once again, all these numbers, all that 925 picosecond doesn't say much. What matters is we have a program. We realize if you use a compiler, this results in 100 billion instructions, some number, and we have a single cycle MIPS processor. This means that every instruction is being executed in one cycle, and the cycle is 925 picoseconds. This is the CPI. This is the number of things. We multiply it, and we get 92.5 seconds. Now, if we want a better processor in terms of performance, we want that the same program executes in less number of cycles. Okay? That's our only goal. Now, the one thing that is working for us are, the simpler solutions. When we look at simpler solutions, the first thing is, if you have 100 billion instructions, why don't I take two processors? The first one does 50 billion, the other one does 50 billion, and they share the load in between them. And hopefully we are done. And you all are taking parallel programming courses. You know that this is a good idea, right? Can you indefinitely parallelize something? No? What's the thing that is your enemy? Who's the... Mr. Amdahl. Okay. There's all these people, and I don't know if these laws are always invented by people who have cool last names, like Amdahl, or, I don't think Gurkaynak law has any chance of, surviving. And then, maybe in your career, you have to take a look at your last name and decide whether or not a law will be named after you. Anyway, they said less jokes, sorry. So this is the first thing that we can do. We realize that that one also has some issues. It's not like free lunch for everybody. But then we realize there is another type of parallelism that can be used, and one that we used a lot also famously for assembly lines, manufacturing cars. That is, instead of looking at the entire operation as one very long, continuous thing that does different things, let's split it up. Let's split the task into smaller subtasks. And the moment I'm done with one subtask, I can already start doing the subtask of the next item, and then the next item, and then the next item. So in total, we realize that what we are processing are tokens, instructions, and the time that it takes for one token to go through my process is not changing. That is the latency we talk about. How much time, how many cycles does it take once I have a new instruction until that instruction is completed? That is the latency. But what you can change, and you can show that this change, I have the slide in a few seconds, is you can increase your throughput. That means that every individual instruction still takes whatever time it needs to complete, but since I broke it down into multiple smaller tasks, I can run things at a faster rate. And at every clock, I will get an output. If I can do this trick, let's say 5 times, this means that my original clock rate was, let's say, 1 gigahertz, and I was getting one result every nanosecond. Now I've broken it to 5 equal tasks, and if I'm good at dividing the tasks into equal-sized chunks, my life would be perfect. Each task would be 200 picoseconds, right? I would run this thing at 5 gigahertz, and within 1 nanosecond, within the time that the original instruction finished, I would have finished 5 individual computations. That sounds like a great idea. That's like a super, super nice speed up. And mind you, it seems that it comes for free, which is where you start smiling. It's like 5x for free. You mean that I could earn 5 times more money without doing anything? Sounds like a spam. And we will realize, well, first of all, anytime you hear such a speed up, things are like, that's ka-ching, you know, that's, I can sell a processor that's 5 times faster, and I'm actually not changing anything. I can just keep my design and do whatever pipelining. Yeah, sure, pipelining, come, pipeline me from beginning to end. Like, it's great. We will see, though, life is not that easy, because there were a lot of issues with this pipelining example, and we started discussing about them. Today we will finish part of the story. The story doesn't end here. The story actually still continues up today. We have been very creative with finding solutions to the problems. Those solutions usually create their own problems. Then we find solutions to those problems, which, you see how it goes, right? We have to eat. Okay, so for the MIPS processor, let me just try to very, very shortly, as a reminder, keep it here. So my issue was that I had one clock cycle where I started, and then I was going down, and then I finish at some point. It was said that this is 925 picoseconds. Good. And I was actually first, when the clock rises, I had the address, so I was fetching the instruction. I was decoding it, trying to understand what it is, find my... Can you reduce the microphone? Rather than me not going to... Yeah, okay. Decoding. And then I executed. I had some ALU operations take place. If I needed to go to the memory, I was here. And then I was writing things back to the register if needed. Now, this thing was taking forever, 925 picoseconds. And then we said, if I can divide this into 5 equal-sized chunks, then I could run this at 5 times the rate, meaning that, hey, this is the first cycle, and then this is the second cycle, and then this is the third cycle, and then this is the fourth cycle, and then this is the fifth cycle. Now, the problem is, so if this was roughly 1 gigahertz, this guy is 5 gigahertz. Did I do it right? 1, 2, 3, 4, 5, yeah. Whew. Okay, so if this one was 1 gigahertz, this guy is bound to be 5 gigahertz. And when you are watching here, this is what we were doing yesterday, with making these things. At every clock cycle, you get one of the results back. It still takes you the entire 5 cycles, more or less, to go through, but when the latency remains the same, but when you are here, you're receiving things at a higher rate. Your throughput is higher. So you are playing this game when you're at pipelining, that you trade off the throughput, and you increase your throughput by the number of pipelining stages. Well, sort of. So the first lie is that every time you are doing this, you have a register here, and this register has 2 effects. First of all, if you remember in the timing that we were looking at, you had a propagation delay here, and you had a setup delay here. And that was coming into your calculation once. When we go back to the slide, you see that that was the propagation delay of this flip-flop, and then you had the register file set up. If I divide it to 5, now I have this thing in every clock cycle. So I have 1 propagation delay here, and I have 1 T setup here. That one comes in addition to the time that I need to do things in between. This is also why, ultimately, you cannot go and make 5,000 pipeline stages, which would be 5,000 times faster, until your competitor comes and says 5,002, whatever. So this thing is limiting you, because after a while, and it's easy to see after when you look at these numbers, so register to clock delay is 30 picoseconds, setup is 20. In this case, 50 picoseconds is the, if you are running this at 50 picoseconds, which is 20 gigahertz, you would be doing nothing else in between. You would just be able to, copy data from here to here and do nothing in between. You would need infinite number of pipeline stages. You still are not calculating anything. Okay, so that one sets a limit. So that was one of the issues. The second issue is, and this is quite annoying as well, this would have worked perfectly if magically all these things that we are dividing were exactly equal. So if this was 1 nanosecond, let's say ignore these parts, if I could make each one of them 200 picoseconds, I would have a perfect pipeline. Now, when you come to a real MIPS implementation, a microarchitecture, these things have their own times. We were calculating the speed at which it was doing. We came up with this 925 picoseconds, and they were composed of these different parts. And, pipelining doesn't have to be 5. 5 was just an observation that these are the 5 very distinct stages. And we said, well, they look sort of kind of similar. So if the single cycle, this is your 925 picoseconds, you say, fetching about 200 something, decoding is close to that, ALU is sort of kind of the same, memory is the same, the write register, well, there we are not doing much. So then you can lay this out and say, this is my clock cycle, 250 picoseconds. So there is one instruction, the memory reads, that require exactly that much. They execute ALU, if you look up this is where it comes from. These are the numbers, right? When we come here, we realize that, okay, the fetch and the memory read-write takes the entire time. This guy is slightly shorter. This guy is a bit shorter. And well, this guy, it's not really taking that much, but what can I do? That was the division that I had. Ideally, I could have reached the maximum speed if these guys were all equal size. Now, if you look at it, the clock cycle will end here, right? So it's 1250. You say, okay, but at every 250 picoseconds, I'm getting a new output. Just by, simple calculation, you can say this looks like it's almost 4 times faster, almost. Not 5, that was the ideal case. Why did I use the idealness? Well, because my individual stages were not completely balanced. Yesterday, when we were making the demos, our friend here was struggling with the cutting. It wasn't that he was struggling, the job was difficult. It's not his fault. Okay, it wasn't Edward Scissorhands, they could just cut it. And, that one caused this. Solutions to that can be found. This is also what microarchitecture people spend a lot of time on. Can I, put some of it into this site? Can I maybe distribute this here? Can I maybe make these things sort of merge into it? And can I remove a pipelining stage? Can I feel everything better? So this is what goes on. And the good news is, because we have all these abstraction levels, whatever you do in the microarchitecture, however you balance them, you get a plus. On the architectural side, however, we still have some issues we have to think about. And this is the pipelining thing that we saw. Now we have 6 instructions. The upper one is the load word. And you say that in the first cycle, we are just loading from the data memory the instruction. We still don't know what to do with it. In the second cycle, while we are reading the registers for the first instruction, so the $0 and 40s actually doesn't come from the register file, but it's a constant. Then we go to the memory and fetch. In the same time, the fetch unit is getting the next instruction. Then we are getting the next instruction while reading out the register file for the second instruction. At the same time, we are calculating the address. For the first instruction, we are reading the memory. We are calculating the addition for the second instruction. Here we are reading, etc., etc. This is how we were showing how these instructions can be laid out. But now the nice news is, once the pipeline is filled, because at this point, I still don't have a result. No result, no result, no result. Here is the first time that one of the pipeline is now filled. It took me 5 cycles, the same latency I had before. But now, at every cycle, I will get one output ready. And every cycle, I'm getting a new output. Now, if you are running something 100 billion times, the first 5 cycles you really don't care about. Right? Things look good. This is why we are doing it. We are very stoked about it. And we say it should be really easy to go from this single cycle architecture into a pipelined architecture, because we say we are dividing the job from here to here. That should be one cycle. So I start with the clock here. I should finish. Let's see if this will match. I will finish my decoding at this point. So what do? We say, hey, let's put some registers in between. Almost. Not bad. Okay. So we say the instruction memory, we start here, we finish here. At the same time, in parallel, we are calculating the next program that goes in here. I pick in the decode stage, I know what my instruction is. I find the operands, I extend this thing. In the next stage, I calculate what my addresses will be. I do the ALU operation. Next stage, I go to the data memory. Here, I just write it back. I either take what comes from the ALU or from the memory, and then end up writing it back to the register. And it wasn't that easy, because this is a data path. This just shows the data connections. But we know that in a single cycle architecture, at every cycle, we make decisions about which input we will choose. Do I write to the memory? Do I select the output of the register file, or do I select a constant? Which address do I write? And that was encoded in the instruction. Now, when you come to a pipelined processor, you also have to pass and pipeline those control signals as your data progresses from one cycle to another. You have to copy them over, because if you are always looking at the current instruction and making decisions about whether or not to write to the memory, well, guess what? The instruction you are decoding here is not the one who's writing the data to the memory. That one was 2 cycles before. So I need to make sure that my decision to write to the memory is passed to the next cycle and to the next cycle. So the signal coming here comes 2 cycles, comes from a decision, from a decoding I made 2 cycles before. Okay? Any questions so far? I wanted to repeat this because when you are taking a look at it, July mode, it seems very, very much like the first one. So the details are a little bit hard to spot. 5 times faster, a bit more complicated. Okay? Questions? I really like that bunch. There's like this one bunch that wants to exit as soon as possible. So there is like a bigger concentration of people just by the door, and I'm fighting hard to make sure that they don't leave. But okay. Now, the story sounded very well. The only problem that we had were these additional setup, whatever times that we don't care so much. That was the only downside. However, we started arguing that there are hazards when we are trying to divide a job into smaller parts. And we saw that we have 2 different types of problems. The first ones are what we call data hazards. We are calculating, I broke down my calculation into multiple steps. And the next instruction may depend on something that is not yet ready. Because guess what? I'm updating my register here 5 cycles after I start. The next instruction that is coming after may already need my instruction, the result of the current instruction. So I cannot continue if I have a dependency on the data that comes before me. And then the second one, which we didn't discuss yet, are the control hazards, and this happens because it's not always sure what will be the next instruction. And what we have is a pipeline that is filled. So there is the first instruction, then he moves here, then he moves here. Well, if he moves here, someone else is coming from behind. It's like this nice orderly line. How do I know which instruction is this if the branch instruction that jumps somewhere or changes the flow of the program, we didn't yet have time to complete what that operation is. I said, if I is larger than 10, go to some other location. Okay, but I barely got the instruction. I don't know what it is. Now I'm decoding. Oh, it's an if. Okay, what do you do if? Well, I need this number and I need to see if it's larger than 10. Say, okay. Let's send you to the execution stage, which makes a comparison somehow. And now I may know what the address is. And here I am sure I know what the thing is. Well, guess what? What's the next one? Well, I'll pick something. Either I'll wait or I'll pick something. And notice that when you're at the end, looking here, your idea was that every clock cycle, you would get one instruction, right? Instructions per clock. Clocks per instruction, doesn't matter. And if you are not completing something because you are waiting for it, there are empty parts in your pipeline. There are what we call bubbles, which increases the number of clock cycles you need per instruction. Now I had a nice single cycle instruction thing, and there was nothing ambiguous about it. I had enough time so that I could do everything about the instruction. It was just taking a lot of time. We got greedy. We said we want to go fast. And then we realized that we have these issues, and I'm paying a penalty for it. I don't, once I saw that much money, I got rich, I got fast. I don't want to relinquish it so easily. So we were starting to talk about what kind of things we have. And we said, look, this instruction, this add, takes S2, takes S3, adds them together, writes them to S0. I know what the instruction is. I have these two things. I edit them. This particular instruction didn't go to the memory, but that was a time where I had to go to the memory. If I'm not going to memory, well, okay, too bad. I'm just passing along. And now I'm writing it back to the register file. S0 is computed and ready, available at this instruction. And if you look at it, it's the sub-instruction that uses S0, S5, and calculates T2. We'll be reading the correct S0. This guy also needs S0. This guy also needs S0. Now, you can make two arguments saying that, Frank, do I really need S0? Maybe I can use something else. Or we'll just wait, or something like that. But it's a problem. This needs to be solved. So for that, there are a couple of, so this summarizes this thing, there are a couple of solutions. And the solutions are, they also have sub versions of how they are being handled, but they fall into two categories. It's either, they fall into two categories. It's not true. No matter what, as a hardware designer, you cannot have it that the program doesn't run correctly if the instructions are given according to the instruction set rules. You cannot just say, yeah, well, you should have programmed it in a way that every load instruction is separated by 1,000 different instructions. Nobody told me that. That's not part of the architecture. If the architecture says these are the instructions, If the architecture says these are the instructions and or sub, and then your hardware should do the correct thing regardless of what condition they are in. Okay, so let's be sure about that. There is no, hey, sorry, you should have done better. But there are solutions that can be done in hardware. You have to have them. And you may pay a price. So one of the things that you can do is stall the processor pipeline. If you realize that this one instruction for decoding needs one of those instructions, one of those registers that have not yet been written, you just stop the previous one, says, okay, stop fetching. I still need that data. Data isn't here, so please stop. So there was this, remember there was this one person here. Are you? Yes? And he was feeding a new data every time. We have to stop this guy and say, stop, halt. I still need to calculate this. I'm stuck here. If I'm stuck here, the next guy cannot do anything. And then most importantly, I shouldn't be fetching any new things. So we halt it while the previous instruction goes ahead. And while the previous instruction goes ahead, I create empty bubbles. That's why we call a bubble in the pipeline. And once the data is where it is supposed to be, once it's good to continue, I can say, okay, S0 is at the place it is. Let's go on. Now, notice that this stalling is not nice, because in the end, when I'm looking at instructions, I'm still seeing something come out, but in our case, 2 of them would be useless. And instead of having 5 instructions in 5 clock cycles, I now received 5 results, out of which 2 were useless. So I had 3 real instructions per 5 clock cycles. My CPI now is not 1 anymore. And this became because I was using a pipeline, and that pipeline had a data hazard, and the way that I handled it was by stalling the processor at runtime. Needless to say, this is the last thing you want to do. If you can avoid it, it would be great to avoid. So the next thing that you can think of doing is, well, the processor won't be doing something meaningful, so maybe the compiler can realize that these are the data hazards happening, because it's known, right? The moment you see the code, compilers are smart. You see here, S0 has to be calculated. This microarchitecture needs 2 cycles for it to come. This is not going to happen. So the compiler could already do something. The worst thing they can do is execute an instruction or schedule an instruction that doesn't really make something useful. That's like this. Technically speaking, it's the same as stalling. The difference is, in this case, the compiler already took care of things. The hardware doesn't have to do, but you cannot design a hardware that has to rely on the compiler to insert no operations. Now, the better story would be, instead of no operation, what if I found some useful things to do? Some things that are not needed now, but do not depend on whatever is in the pipeline. Maybe the compiler can juggle things around and do it. Now, when we go forward in the lecture, you will see that we are also doing such solutions in hardware where you look at a larger chunk of code and try to figure out what would be the best order of instructions, so that semantically you are doing exactly the same thing. You're not breaking the computing, but you are reordering them according to, let's say, your capabilities. And now the other thing that we were looking at was, we realized that, I'm writing back the register here, but the result is already available after I calculate the ALU. The number is already here. So maybe I could bypass this waiting and, secretly on the side say, I have the S0 here. And this was actually the part where we were discussing. So this was the no operation issue, and this was the data forwarding, where we realized the first add instruction after the ALU already has the value, so we can find instead of going the regular path, could insert it here, or for the other instruction, before writing to the register file, could directly write it there. Both of these things required hardware that came into the system, and we had to pay the price. Another version was stalling, where you realize this is happening. So you said, hey, I'm going to shift these instructions, stall until I have a solution, because there are some cases where forwarding just didn't work. Again, this thing didn't come for free. We had a stalling hazard unit at the bottom, which is looks at the instruction, the order of them, realizes that, hey, I don't have the data. Shall I forward? Shall I stall? And do things like that. Sorry for the repetition. I just wanted to make sure this is clear. We can take a break, and then we continue with the control hazards. Now it's better. Okay. So in the break, there were some questions. Once again, I cannot emphasize this enough. This one tells you a lot where you want to go, why you want to go there. So if we are not covering the multi-cycle architecture, which is in the book, if I say we are not covering, we are also not asking it in the exam. Great. But that one is, for example, sacrificing the clocks per instruction for a smaller area. That's what it does. That's the reason behind its existence. So, you know, you already see that sometimes things that you do here for making it better make it worse here. So this always stays. So there's a constant friction, let's say, between the cycle time, what you do within a cycle, and how many instructions you need. They're all related. So if you pull one, it's not independent from the others. You push the other one around. And the goal, the nice goal, is to find something that is a good compromise between all of them. Now, there was also one more question just to emphasize. First of all, if you have such an if you have such a microarchitecture, if you decide that this particular diagram, let me just go to it. This particular diagram is your pipeline processor. You have to deal with the consequences of problems. It's your job as a hardware designer. You cannot get away with saying, yeah, this will work if the instructions have the following restrictions. Don't put an add after a load word, or don't do this within 2 cycles of that. That's not, I mean, hardware designers cannot get away with this. It's not like, you know, you can just roll out some software and then issue a patch 3 days later. Sorry? That's what they always did. Somehow people accepted that this is an okay thing to do. With us, they did not accept it from the beginning, and somehow the hardware designers did not get the memo. So we are condemned to make sure that no matter what is in the instruction memory, as long as it is described in the ISA, in the architecture, I have to make sure that it works. So if there are 2 instructions that come one after another, and they depend, there's a data dependency, I have to have a solution to solve this. I may need to stall, and then I need to stall, okay? And stalling is in hardware. I realize that I cannot execute, I cannot finish this stage because I lack the data that is still in transit. And I cannot have any more instructions coming. This is a hardware thing, and I need to somehow separate these 2 instructions and create enough distance between them time-wise so that this instruction has the time to finish and write back, and then only I can continue. Now, with software, I could maybe help it. I could prevent these things happening. I could prevent the hardware from stalling. And yes, the worst thing I can do as a compiler for trying to fix this is inserting instructions that don't make any sense, useless instructions. For all I care, they could be called no operation, meaning that the instruction set architecture contains specific instructions that tell you don't do anything. Or they could be instructions that result in no effect. Like you XOR the same number to itself and write it back to itself. You know, if you XOR any number, XOR A XOR A, written back to A is 0. You know, you don't create anything. There's nothing interesting happening there. It's an operation that you could live without. But the compiler can say, okay, you know what? I need 2 instructions in between there because there's a data dependency for this implementation. And let me find some instructions. And says, hey, instruction, what can I do? Can I add? Can I OR? And say, okay, worst case, I'll just no operate them. I mean, I'll just put an instruction that doesn't do something. This is the end effect. If you are just watching the result and you are just, you know, what is this processor doing for me? You realize that stalling and no operation may have the same end result. That doesn't mean that they are the same, okay? Because the processor just takes an instruction and executes it, sees that there is no data dependency, and everything goes forward. It doesn't need to make something. And the compiler chose things in a way that the hardware does not need to do something. And the compiler is not doing it for the love of the hardware, certainly not. The compiler is hopeful, it was in an optimization stage where it thought that he could find some good instructions, but was unable to do so because of some constraints. Meaning that it is actually, I mean, there is much more potential in it, because for a given time, for one instruction, for one stream of instructions, maybe he couldn't find the instructions and ended up using no operations. But in some cases, he might be able to squeeze 1 or 2 useful instructions in there, which is better than a stall. Did it sort of make sense? I am not so sure. Can I see some thumbs up or down? This is up. That part is completely zoned out. No? Okay. Okay. So let's come to the control hazards. This is where we actually... Okay. Now, the control hazards do not have something, I mean, they look very similar, so it's a good exam question, understanding comprehension question, explain the difference between data and control hazard. For those of you who are complaining that I am not solving any exam questions in the class, I do all the time. I say this is a great exam question, right? So it says this is something that could show up. It's even future looking, not past looking. So what's the difference between a control hazard and a data hazard? In a data hazard, the issue is that a value I will use in the next instruction isn't ready yet. In the control hazards, we have certain instructions that change the flow of the program. We want to have loops, we want to have if then else statements, case statements, while loops, and all of these essentially boil down to the fact that we will modify the program counter. He will not be showing directly to the next instruction, PC plus 4, but at some point we are going to say, hey, let's jump somewhere. Now the problem is, I fetched an instruction. It says branch on equal to. Say, oh, okay, great. You will branch on equal to. Now I'm decoding and I'm trying to find out what is equal. It says pick these 2 registers. I say, okay, let's pick S0 and T0. I have them. Now let's compare them. Are they equal or not? And say, oh, yay, they are equal. I'm going to jump. But there is one instruction after me that's being decoded. There is another one that I just fetched. And I just realized now that I will branch. These 2 instructions behind me are not the ones that should be there. Maybe. Right? Depends on where I'm branching. So that creates a control hazard. And so the branch is not determined until the 4th stage of the pipeline. I have to finish this. And now I know what the value is. And instructions after the branch, so the instructions that filled the pipeline, are maybe not the instructions they should be there. And if this is the case, this guy speculatively executed things, just realizes, oh no, we are not going this way. Really? Like I did all this work, like I fetched instructions, I even started adding, and now you're telling me this is not correct? And then you say, sorry, everything we did here, let's start over. And you go here, forget everything you did before, and you start again. Now, this one is a branch misprediction penalty. I have to flush a number of instructions when the branch is taken. So I have made a decision, I have made a bad decision whether or not I'm taking this branch or not. Now, one question that will come is, if you have a branch, why do you keep on fetching some instructions? You know, why don't you just wait until this guy goes and decides what's the next instruction and don't fetch anything until the branch is done. You know, that would have been the smart idea. Why do you think I do this? Anyone?
I guess if we get it right, then we are a lot faster than we.
Yeah, we are greedy, right? We say, I want to execute as many instructions as possible. For every clock cycle, I want to be executing one instruction. And I have this great pipeline that made it 5 times faster. Okay, I want one instruction every cycle. Guys, you know, if the moment I see a branch, I just don't do anything, I'm losing some of my CPIs, some of my clocks are not producing nice instructions. And it goes back to my thing. It's just an average of how many times I'm doing this. Now, the good story is, if I'm good at predicting if the branch is taken or not, if I make good choices, I might be right most of the time. And I could reduce the penalty taken for my mispredictions because I don't mispredict often. So the question is, what kind of predictions can I use? And I realized that I was a bit, oh, there's a question. This was here for a long time, probably. Oh my God. 15, oh no, it's just a new, okay, I'll answer that in a second. So, question just threw me off. So I'm trying to set up a system where I try to do as good as possible. And now the question is, can I have some ideas how I can do this better? And I was looking at the lecture and said, hey, Frank, you have 15 slides for today's lecture. How will you talk for 2 hours? People want to listen to you to 2 hours. They don't want to go home early. So find something. And I looked at the lecture notes from last year. Onur can go through a lot more slides than I can in a thing. I looked at the this lecture, 183 slides in the slide set. I won't be able to do that. But what I wanted to say is that this is a very, very active research question. Even today, there are the bigger conferences on computer architecture, ISCA. Papers are published on how to improve the branch prediction, how to make sure that I pick right most of the time. And the simpler ones have already been taken care of. Those are the 180 slides. But there are a lot more things to go. Yeah, sorry.
So what happens when we do this predictive execution, I guess, and we write to memory, then we realize that we want to take a branch. Wouldn't we have to like clear the memory again? And
yeah. Very bad idea. No, it's not. I mean, see, it's the hardware's job, the microarchitecture's job to do things right. Now, the good news is, especially in our case, the memory access comes quite late. The update of the write-back is quite late. So the branch is ahead of me, and the bad instructions are behind me. So they are not overtaking me and writing something to the memory. But in a different architecture, if I already updated some registers and the things were made based on this, I have to reverse everything. And if I have to reverse everything and I don't know what I did, I am in trouble. So I need extra hardware to sort of kind of go back to a checkpoint where I know what the state was and replay it. And that all comes back to the penalty I'm paying for doing this. Now, when you go forward in the lecture, we will find architectures that don't even do 5. They want to do 20 pipeline stages. They want to break down fetching, decoding into multiple cycles, sub-steps, and things like that. As the pipeline gets longer, I have more things in the pipeline, I am more susceptible to problems here. Because if I have 5 pipeline stages, the chances of, you know, multiple bad things happening is not so bad, is not so high. The longer it is, the more likely it is that I'm making a mistake. Other things that we are doing, which is orthogonal, is maybe getting multiple instructions at the same time and executing 5 at a time, and then pipelining them. Imagine that you have a modern processor, which happens, has 20-stage pipeline and tries to execute 5 instructions in 1 clock cycle. So in the pipeline, you have 100 instructions. And there could be all kinds of dependencies in between them. Somebody has to take care of it. So now I just have to see the question, wouldn't unsafe hardware with strict rules such as no add after a load word be more performant? Basically, the question is, couldn't I sacrifice a little bit of the flexibility of what programs get executed, put into the memory, thereby making a simpler hardware so that the hardware is more performant and I put more rules? That is definitely possible, but it goes back into the instruction set architecture. The architecture has to say, this is the way we work, because the software, the compilers will look at the architecture description, and whatever is written there is the code, is the Bible. That is the way it will be realized. Once you have this, once you agree on this, microarchitecture has to implement it. MIPS doesn't have such a thing. The data, and notice that it's my greed in the microarchitecture that results in us coming up with this 5-stage pipeline. Nobody said I have to make a 5-stage pipeline. The architecture is agnostic to how I implement it. It says, this is the instruction executed. I had this great architecture, single cycle. I take the data, I modify it, I know what the branch is, and the next thing, it takes me a while, but when I come here, when I start the next instruction, everything is done. I got greedy. This is why I'm paying the price. Now, there is a penalty if I don't know what instructions are coming behind me. The deeper the pipeline, the more penalty I will pay. And the question is, can I do better? And there are some, so this is in the textbook. I'm just going to stay with those ones. So this is my original pipeline. Well, not really. This is my original pipeline plus all the forwarding things and all the stalling signals that I added to it. It got a bit more complex than the first time we were seeing it. There's a lot of pipeline registers in there. There is, you see, additional multiplexers that popped up. There are all kinds of additional registers to forward it, enable signals, clear signals coming so that we can insert bubbles, stall pipelines, and things like that. So we got a little bit problematic. And here is the one example. We realized that we are at address 20. So we pick the instruction. It will compare T1 and T2. And if both of them are equal, I'm going to jump 40 ahead. So the next instruction would have been 24. So instead of picking the instruction at 24, the instruction, assuming T1 and T2 are equal, would have been this guy. So I picked the first instruction, branch equal to. Somehow there's a typo there that says load word. The next cycle, I pick the next instruction. Now I don't know anything about the branch yet. And I'm saying, maybe I won't branch. I mean, what are the chances that T1 is equal to T2? How much money are you going to put on it? You say, okay, you know what? He never branches. I'll just go on with the next one. So I'm starting to say, let's pick the AND. This guy is doing his computations, and then the way the branch equal to goes, if you remember, we were subtracting the content of those two registers, and then we were checking if they were the same. And then if they were the same, then we would say, we would raise something and then modify the program counter. And only then I realized that, hey, all these instructions that I fetched in the meantime, the AND, the OR, the sub, are useless. The next instruction, actually after the branch, is the set less than. And now I have to jump here. All this work, gone. I have to clear it away. And I will say, sorry, I had 3 instructions that didn't do. Happens every now and then. Question is, how often does it happen? How often do I have a branch? So this one goes back to, and having this means that every clock cycle, I'm not having one instruction. I'm 5 times faster due to pipelining, but I'm losing some of my performance because some of those instructions have misses. And you can take a look at why am I designing this processor? Is it supposed to run a game? Is it supposed to run a browser? Is this browser going to certain web pages? Is this an AI algorithm that has for I, for J, for K, something like that? What is it? And that one can give me a mix of instructions. And depending on those, I may calculate what is the likelihood of me having branches in my code. How often do I have them? Is it 5%, 10, 20%? And if I look at it a bit more closely, I can realize how often do I make a mistake in them. Now, in some of these things, we can even say, look, the moment I have these 2 registers, I could do something. I could just compare them without going to the ALU. Maybe this is such an easy operation that I could squeeze this in. Now, this assumes that I have some time in this pipeline stage, and I add like some extra instructions in here, and extra hardware in there to compute it so that I can have an early detection of the branch being equal. This could work because you may remember, the equality circuit is something that you did very early in this in the exercises, right? You had a bunch of XNORs parallel, and then you ended them together. For 32 bits, if you have just ANDs, 2 input ANDs, that's 5 stages of ANDs, log to N, and then 1 XOR. Maybe looking at your timing and things like that, you say, maybe I have enough time, and I could, in time, resolve this thing. And this would mean that when I come here, I have fetched AND, but already in the second cycle, I know where to go. So I saved 2 instructions from being flushed. I'm only flushing 1. Could I flush a bit more? What kind of additional control things do I have to do? Well, I still have to flush this instruction. I'm not completely free, but this little, let's say, thing could have helped me. Now, this is also a little bit circumstantial. It doesn't mean that all instructions, all branches, all control hazards can be solved like this. MIPS is a bit special. It only has a branch if equal to or branch if not equal to, so the same type of hardware could be used. There are a lot of processors that have complicated branch instructions. Less than something, and less than, you realize, cannot be calculated so fast because you need to subtract them. You need an ALU operation, which takes much, much longer. And now, the other thing is, I might have been better at picking the next instruction. So what did I do currently was saying, you know what, if I don't know anything else, I'll just keep on fetching the next instruction. So I was here, and the next instruction will be PC4, the next instruction will be PC8, the next instruction will be PC12. I will go like that. So this is sort of kind of the best thing I can do if I don't know anything better. Okay? I could do different things. So this is assuming that no branch will ever be taken, right? That is what it is. I can just say, hey, I'll assume that the branch will never get taken. You could also do the opposite. You can say that every time there's a branch, I will assume that the branch is taken. Why not? I mean, it's 50-50, right? If you don't know any better. So this is the interesting thing. Do you know any better? Who knows any better? Any idea? Yeah? Yeah, and then the compiler, knowing the decision of the architecture, if this guy is taking is assuming that every branch is taken, or if every branch is not taken, you know, it's a decision, can generate code. So instead of using branch if equal to, can change that to branch not equal to, knowing how the person does. But we can actually make a lot of different things. For example, we can look at, if you remember 2 weeks ago, we were looking at programming, and we had a bunch of loops. And we said, these are the more common loops. And one thing that we might have seen is that the loops usually end up jumping backwards. You know, you do some operations, and then you go back to where you were, and then do something else, and then go back. So as long as you're in the loop, you are jumping backwards. And you only go out of the loop by, you know, not the thing terminates, and then you go forwards. And then you can say, hey, you know what? Maybe let me take all backward loops, all backward branches, but not take the forward branches. Now, I'm deviating from my PC+4 behavior, and I'm saying, hey, I can be better. Does that make sense? Is it too nebulous? That part is already in the weekend. That one is good? Okay, thank you. Great. Now, there are even better ones, and it boils down between how much do I do in the hardware, how much do I do in the software. Now, the good news is, when you go back to such an architecture, you realize that this is a part that does PC+4, right? So this is my program counter. And I have maybe another adder to add the sign extended version, but the pipeline is quite empty, or is not so full in the parts that is calculating the next program counter. There's not that much happening. I mean, the computational intensity there is not very great. So I could actually go a little bit more crazy in there. So what if I actually looked at the history and said, when this program runs and I have a branch instruction here at this address, so I'm just going to make up an address, I'll write it short, and here there was a branch equal to, and it goes plus 40 to here, so wherever that is. Don't make me do the calculation. Oh, let me do it. 47. Okay? There is such an instruction there. Wouldn't it be great if I somewhere kept statistics about how this branch is doing? Just because I have so many transistors lying around and I could make use of it. I'm greedy. I know that every misprediction is costing me, so I'm trying to think of better ways of making use of the hardware so that I don't mispredict these branches so often. And you say, sure, I can store a few bits somewhere, and that says the instruction here, this branch, the last time took the branch. And you say, hey, if it took the branch last time, maybe this time you will take it again. And that could be my prediction model. Or I could have any kind of other algorithm that helps me figure out what is a better way of predicting the next move. Now, this gets quite complicated, right? So the software could already rewrite the software in a way so that the prediction is better. The hardware could start doing it more. And the problem here is a little bit twofold, because you say, that's not the only branch. There is maybe another branch at a different address, and that one has a different characteristic. So let's have 1008. So this branch here was not taken. So maybe I need to store them in a place. I have a little table where I keep the predictions of those branches. How large is this table? Well, you know, I don't know. How much can I afford? How much can I afford means two things. how much time do I have to, calculate these things and go through the table, and how much cost in terms of area, transistors, power I'm going to have. How greedy am I to get the most performance out of it, to increase my my counts of useful instructions versus the instructions that didn't work out. So this is something that I go down. Just to give you something, what is used a lot is what we call a 2-bit predictor. And they realized that having one state, 1 bit of whether or not it was taken or not taken wasn't a good idea. So what they have is usually 2 bits. And let's say this was taken, and this is the taken part, and you use 2 bits. And you say, if we are here, and if it is taken again, I move to this state which says strongly taken. And then this is the weakly taken. If it is not taken, we move back. If it is taken, we stay here. And then we have the not taken parts. Again, weak and strong. And if it is not taken, I go here. If it is taken, I go here. If it's not taken, I go here. If it's taken, I go here. And not taken, I stay here. So instead of storing in the history only 1 bit, was this branch taken the last time or not, I'm giving it a little bit leeway, saying that if it was strongly taken, and then once I don't take it, I'm still going to predict that the next time it will be taken. I'm not completely changing my mind, saying that was an honest student, was coming to the class, did do something silly the last lecture. I'm not going to judge him by once, but if he does it twice in a row, then I'm going to go and say, I'm not taking this guy. And if you are here, one nice thing, so one good, you realize I predicted this branch is not taken. I realize that this wasn't the case, and then say, okay, I'll be in the taken part. If I am strongly believing that the branch is not taken, if it's taken once, I'll still not take it the next time. But then the next time, if it still continues, I'll be here and I'll stay in this thing. So there are a lot of research going in devising roles like that and making, and what happens now is here you have 2 bits stored in a table for every one of them, every one of those branch things where you keep the history and saying, how did it happen? What happened? What was the last time I was looking at this branch? And based on that table, you determine what the next instruction will be. Now, if the branch is taken, you should also know what address it was so that you can also store it. So you say, hey, this is taken and it was going to this address so that you don't have to do these things. You keep a pre-computed values from the last time and you store it somewhere. And this guy, while he's fetching these things, before you fetch the next instruction, you're already calculating this. A lot of work, a lot of effort goes into these prediction techniques, and the larger, the deeper your pipeline is, the more instructions you are fetching, the more important it is that you do a good job here. So this is why a lot of the discussions and effort goes into this. Now, this gives you a basic summary of what kind of things happen. Now, the thing that we wanted to see is what's the performance, right? It will all boil down to this thing. And now we were asking what was the instructions that you were considering? How many branches do I have? How many adds? How many loads? How many stores? Well, people came up with benchmarks, and they argue about these benchmarks all the time. Spec in 2000 is one of them. And if you look at it, 25% of them are loads, 10% of them are stores, 11% are jumps, branches, 2% are direct jumps where I'm not making any decision. I know I'm jumping. And 52% are R-type instructions when compiled to MIPS. Now, is this the one and only thing you should be looking at? No, I mean, but people agreed that, or some people, some community agreed that this is a good one. If you are in a specific domain for machine learning, there might be more specific benchmarks that represent this a little bit better. If you're doing signal processing, maybe there is something else. If you're doing database management, there might be different benchmarks. Regardless, you might have something like this. And now you can make some predictions about it. You say 40% of the loads are used by next instruction. Well, if this is the case, I have to stall or I have to do something. And 25% of the branches are mispredicted. And if I have a jump, the problem is I fetch it, and next instruction I know I'm jumping. I already fetched one more instruction that I have to delete. So this comes out of my design. What is the average clocks per instruction? It used to be that it was 1, but what is it now? Now we have to do funny things. We say load and branch is 1 when there is no stalling, and 2 when I am stalling, when I have an issue, a dependency. And now you look at it and you say, hey, for the load word, 60% of them are single cycle instructions, but for 40% of them, I need 2 clock cycles, 1 for make the load and 1 to stall. Not like I want to stall, but this is a consequence. So my clocks per instruction for load word is no longer 1, it's 1.4. And this comes out of the statistic of the program that I'm considering to execute. The same one goes for the branch. 75% of it I predict well. I could improve this if my prediction algorithm was better. If I was doing those 2-bit things, I could maybe increase it to 90%. But whatever, 75% is 1, but 25% is 2 cycles. So my average is 1.25. Now, how do I calculate my average CPI? Well, I say these are my load instructions. They require 1.4 clocks per instruction, and 25% was load. The store, well, the store always seems to work, and 10%. Branch, well, 11% of my instructions were like that, and I had 1.25 on average. Jump, well, the jumps were always 2 cycles. I had no choice. And the R types are 1. And I multiply and accumulate this, and I realize that my base CPI is now 1.15 over this entire benchmark. Notice this depends on the type of instructions, the quality of my stalls when I'm doing load words, when I'm doing branches, and the statistics, how much I am wrong. In some cases, like the jump, there is no choice. Jump, we didn't really go into detail, but you can easily see it when I'm jumping, because I have one cycle where I fetch and the next one where I decode. The moment I decode, I realize, hey, oh, no, I'm jumping, but I already fetched one instruction, so that one has to be clean. Now, this is the CPI part. Remember the part where I was telling everything is about the N times CPI times clock cycle? So the CPI part, I calculated 1.15. Now, what about my timing? Now, I divided my pipeline into 5 stages. I have these 5 stages: the fetch, decode, execute, memory, write back. Whichever is the longest will determine my problem, right? One of them will be longer than the other one. So it's either the fetch stage, this one. Now, in this particular exercise, an example, there is a funny quirk. And the funny quirk is the decode and write back use register file, and they have only half a clock cycle to complete. They organized it so that in the first half of the cycle you write, in the second half of the cycle you read, and they want this to be 50-50. It's a special quirk of this particular implementation they use in the book. And because I don't want to create another exercise, I'm just sticking to them. This is why they have the 2 in front of it every time I access the register. So the first one is during the decode, where I have the register read, and the second one is during the write back, because they don't give it the entire cycle, only half the cycle. Essentially, you are comparing 2 times the half cycle to the full cycle of the others. Sorry. Okay, so one of them is longer than the other one. And how will I figure this out? Well, I have the numbers here. I have to put them in. And then you end up realizing this register file read tmux equal to and mux setup all combined together give us 550 picoseconds. That's quite a lot, but well, it is what it is. If I don't like it, I can go and create another architecture. But now I have my numbers. I have my CPI, 1.15. I have my cycle time, 550 picoseconds. It's the same program, 100 billion instructions executing on a pipeline. This one didn't change. CPI is 1.15. And this is now my clock period. I multiply it, and I get 63 seconds. Now, I'll show you the last slide. Now, just disregard the multi-cycle. The single cycle was 95 seconds. The pipeline is 63 seconds. So I started this story by saying that, hey, I could pipeline it 5 times. I will be 5 times faster. Does that look 5 times faster to you? No. I started wasting a little bit because the CPI is no longer perfect. I wasted a lot, actually, because theoretically, you know, this was almost 1 nanosecond, 925. So if you think about it, each stage should have been 200. And if each stage completed in 200, this would have been perfect. The stupid thing is, one of those stages that we thought is such a great idea ended up being 550. So I am running this clock, instead of at 5 gigahertz, I'm running it slower than 2 gigahertz. So this is what is killing me, actually, more than the thing. Now, David and Sarah, don't be mad at me. It's a horrible example. It's a bad choice in the microarchitecture how the register file was made, so that the decoding phase takes much longer than any other phase. It's not fair. So it is very similar to what we were doing here. If you remember the pipeline, poor guy cutting was spending a lot of time, and everything was waiting for the cutting to finish. Exactly the same is happening here. We are wasting actually a lot of time in the decoding. And because of that, the performance looks awful. Even if we manage that somehow, we still wouldn't come to 5 because our CPI is not 1. We are losing in CPI. Even if the CPI was perfect, we wouldn't actually manage it, because once we divide it, we still have overhead due to the additional setup times in the divided pipelines. So we still would maybe not reach 5, but you know, if we do our job properly, we could probably, even in a simple architecture like this, easily reach 3, 3.5. If we are only managing 1.5, things are difficult. Now, as you increase the pipelining, getting this number to be ideal gets more and more difficult. Imagine that you had only 2 pipeline stages. You wouldn't have so many mispredictions about one or the other, and you would be able to have a higher CPI, first of all. And second, you would probably be able to divide it better into 2 halves rather than trying to find these things. So the more you go, the more we have. So what did we learn? We learned the pipeline architecture. We saw what the problems are. We saw solutions to hazards, at least the philosophy between finding the solutions, and we discussed the performance of pipeline architectures. Starting next week, it will be the group of Safari. The assistants will take over. We have great presentations where the architectures get more modern. So you saw the textbook examples, and we will see what kind of other tricks we do to improve the performance. We will start by memory, looking much closer at the memory, how we read it, how we can make things faster. And then we will move into better architectures, things that work in parallel, do more in one cycle, then to vector processors do even better and nicer things. Thanks a lot. It was a great fun being with you, and I hope you enjoyed it. I'll be in some of the other lectures as well. And yeah, that's it. Thanks a lot.